This is AP Calculus BC, and in this video, we're going to talk about the radius and interval of convergence of a Maclaurin series and a Taylor series. So last time we really focused on the idea of writing a series to model a function. What we're going to focus on today is once we have that series, how do we know where it's a good model of that function? And that's what the radius of an interval of convergence is really going to represent. So the first thing here is just kind of a quick overview of what we're going to be doing. It says finding the interval of convergence. And let's say we've written a series out and we want to know where this series is going to converge to the function that we're trying to model. So it says here, for what values of x does this series from n is 0 to infinity n factorial x to the n converge? So let's say we wrote that to model some function. Well, notice the terms that we have there, 1 plus x plus 2x squared plus 6x cubed and so on. So we've got some sort of a power series here. It looks sort of like maybe like a geometric type of series, but not exactly the same. So that's kind of the idea. So what we do is we use the ratio test. And remember when we talked about the ratio test, I told you that I wanted you to do it with absolute value. So we were looking for absolute convergence. And the idea here is we can use that absolute convergence test with the ratio test to actually find the interval of convergence. So what we do is we take the ratio of consecutive terms, we take the limit as n goes to infinity, and then from there we can figure out, based on what happens with the limit, we know that that limit, in order for it to converge, the r value is going to have to be less than 1. And so if we get an r value that is equal to 1, obviously that's not going to be helpful. That means that the ratio test tells us nothing. But if we get an r value greater than 1, that tells us that the series diverges. So in this case, when you go through and you simplify everything down, what you get is you get this simplified form of your ratio. So we have n plus 1 times the absolute value of x. Well, as n goes to infinity, that's going to get infinitely large regardless of what x is. So that means this limit gets infinitely large. So the only way this series is going to converge is at the point x equals 0. So this is kind of our worst case scenario for writing a series. So our series is only a good model at the center point. In this case, the center point was x is equal to 0, and our series converges only at the point x equals 0. We'll talk about the results in a minute, but the main thing is we actually are going to use the ratio test every time we try to figure out the interval of a convergence for a series that we write. Okay, so when we think about a series converging, so for us, since we're using a series to model a function, what we're thinking about in our case is, when does our model look like our function? So you can see here we've got this second degree polynomial that we've gotten from our series, and we're trying to model this function. And it looks like these are pretty close as long as we're on this interval, right? Maybe somewhere between, maybe we could go as far as 0 to 4. So we've got roughly the interval 0 to 4 where we look like we have a good approximation. So that's what we're trying to determine, is where does that model that we've written, where does it look like our function? Okay, so let's take a look at an example. I'm going to kind of walk you through this step by step. So this is a little bit of a process, and you'll see that all of those series tests that we were doing, this is where they're going to come into play. So it says, for what values of x does this series converge? So we've got the series from n is 1 to infinity, x minus 3 to the n over n, and we're going to start with our ratio test. So I'm going to do the limit as n goes to infinity. And I'm going to do my n plus 1 term, which would be x minus 3 to the n plus 1 over n plus 1. And remember, I'm going to divide, but I'm really just going to flip that nth term and multiply. So it's going to be times n over x minus 3 to the n. And I want to take the absolute value of that. And when I solve this out, I'm going to simplify that expression. I'm going to get the limit as n goes to infinity. And this is going to simplify down into x minus 3. And I'm going to leave that in the absolute value, and you'll see why that's really important in a second. The n values are always positive, so they don't really need to be in the absolute value. I can leave them in there if I want, but I can also take them out. So I put that times n over n plus 1. As n goes to infinity, n over n plus 1 is going to approach a value of 1. So essentially my limit is just x minus 3, absolute value of x minus 3. Well, in order for this to converge, that means we need to have a value of less than 1, right? That's our ratio test tells me that that ratio has to have a value of less than 1 for convergence. Well, there's a couple of ways that you can go about this. The easy way to do this is to understand where the center point is and to understand what this expression says. So this is telling me the distance between x and 3 has to be less than 1 unit. So that's essentially telling me that I've got a center point at 3. I can go 1 unit in either direction. So when I do this, I just say, okay, well, this is basically telling me that my x has to be between 2 and 4. However, if you can't read those in that way, you can also break it apart. If you think back to Algebra 2, when you did absolute value inequalities, you could say x minus 3 is less than 1 and x minus 3 is greater than negative 1. And when you solve this out, you'll get x is less than 4 and x is greater than 2. And then put those together, you get the same thing I got before. But I would prefer that you be able to read those absolute value inequalities and understand what they're saying. Okay, so at this point, I know that my interval is between 2 and 4. Now, that tells me some information. That tells me my radius of convergence, which is essentially how far can I go from my center point. My radius of convergence is 1. I can go 1 unit on either side of that center point from 2 to 4. Now, notice it says that the radius of convergence is half of the interval of convergence. So what I have here is the beginning of my interval of convergence. So for my interval of convergence, though, I've got to test endpoints. So I have to decide, can I include the point at 2? Can I include the point at 4? Well, now let's look back at how do we evaluate that? So we have really 4 possibilities, right? We could have none of the endpoints being included. We could have one of the endpoints or the other endpoint, or we could have both endpoints included. So there's really 4 possibilities here. And the way that we evaluate this is we just look at what happens at the endpoints. So go back to your series. When we're at x is equal to 2, if I plug 2 in for x, this series becomes the series from 1 to infinity. And now instead of having x minus 3 to the n, I have 2 minus 3 to the n. And that's all over n. And if I rewrite that, that's the series from n is 1 to infinity. And I've got negative 1 to the n over n. Now, this is where knowing those series tests is a big deal, because now we need to be able to tell, is this going to converge or diverge? Well, I know just by looking at this one converges, right? And the reason I know that is by the alternating series test. Oops, alternating. Okay, so that's really what we want to be able to do here, is we want to be able to tell right away, is this going to converge or diverge? Okay, so that's one of my endpoints. Now we want to do the same thing at the other endpoint. At the other endpoint at x is equal to 4, this series becomes n equals 1 to infinity. We have 4 minus 3 to the n over n, which is the same as n equals 1 to infinity. We have 1 to the n, which is essentially just 1 over n, right? So that means that this diverges. And we could do this in a lot of different ways. We could say it's the harmonic series. We can use the p-series test, whatever you want. I'm going to use the p-series test. We could also use the integral test. The main thing there is that one diverges. So it converged at 2, it diverged at 4. So in the end, we've got 2 pieces of information. Our interval of convergence goes between 2 and 4, including the point at 2, and the radius of convergence is 1. Okay, so again, think about what that means. That means that if I write this series to model my function, my center point of 3, I can go 1 unit on either side of that, and I can get whatever accuracy I want for that function. Now, the further I go from the center point, the more terms I'm going to have to use to get the accuracy that I want. But I can get a perfect model for my function anywhere between 2 and 4, including the endpoint at 2. Okay, so that's really what we're trying to do. So last time we wrote the series, now we're trying to figure out where is that series actually a good model. Okay, so let's go through what the results can turn out to be when we go through this process. Because the process itself, you'll find, is fairly straightforward. It's a little bit involved, but it's fairly straightforward. So there's 3 possible outcomes. We could have the series only converge at our center point, which is what we saw on that one at the very beginning. That's kind of our worst case scenario. That means that it's only good at a single point, which means essentially our series is worthless because we already know the function value at that point anyway. So if we only have convergence at a single point, we might as well not use that series to model our function. So the next one is the series converges for all values of x. B here, that's our best case scenario. You can see it's shown down here. That means that if I'm looking at a number line kind of showing my interval of convergence, my interval of convergence is everything. So that's our best case scenario. But then the third scenario is like what we just saw. We are going to converge on some interval. So we can go some distance away from our center point, and we can go the same distance on either side, and then we have to test the endpoints. You can see on this one, they didn't include the endpoints, but sometimes we'll include them, sometimes we won't. We're always going to have to go back to our series test to figure that out. Okay, so let's go through a couple of examples here so you can see how this works. Okay, so what I really want to focus on here is what I expect you to show on a problem like this, because you'll find that for the most part, this is not that difficult to do. However, there are key steps that have to be there in order to justify what you're really doing. So on this one, we've got an alternating series, and what I'm going to do is I'm going to take the limit as n goes to infinity, and I'm going to take the absolute value of this. I've got -1 to the n plus 1. Now, be careful with this when you add 1 to the n here on the x squared, because that's going to give me x to the 2 times n plus 1, or the 2n plus 2 power. And then in the denominator, I've got 2 to the 2n plus 2 power. And then I'm going to have n plus 1 factorial, and that is squared. Okay, so then I want to multiply by the reciprocal of the nth term. That's 2 to the 2n times n factorial squared over -1 to the n x to the 2n. Okay, so that's what I'm using as my ratio test, right? So first thing is, these -1s don't really matter anymore, so I can kind of throw those out. So let's rewrite this in a simplified form. So this would be the same as the limit as n goes to infinity. And looking at the x parts of this, I've got x to the 2n plus 2 and x to the 2n in the denominator. I also have a 2 to the 2n and a 2 to the 2n plus 2 in the denominator. So looking at those two parts, I've essentially got x squared over 4 if I simplify those two parts down. And so I've dealt with these. I like to cross them out as I use them to make sure that I've simplified everything down that I need to. And then the last part of this, I need to deal with these factorials. Well, in order to get the n factorial squared to cancel, I'm going to have to get the n plus 1s out of those two n factorials. So what it's going to leave me here is 1 over n plus 1 squared. Okay, so now let's think about that. If I take the limit as n goes to infinity, the x squared over 4 is going to be some value, but 1 over n plus 1 squared is going to approach a value of 0. So that means that this is going to give me a value of 0, which is less than 1. So that tells me for any value of x, this is going to converge. So my interval of convergence, we can just denote with an I. In this case, would go from -infinity to infinity because it converges everywhere. And if I wanted to name my radius of convergence, we usually use a capital R for that. My radius of convergence in this case is infinite. Okay, so my interval goes from -infinity to infinity, and my radius is infinite. Now, had I had an actual interval that showed up with numerical bounds, finite bounds, then I would have to go through and I would have to test those endpoints like we did on that previous problem. So I've got another one here that I want you to try. And what I'm going to do is I'm going to pause the video. I'm going to let you try to work it out. And now keep in mind, when you solve these out, you need to make it really clear what you're doing. So when you're testing those endpoints, make sure you make it really clear that you're testing those endpoints. So pause the video. When you come back, I'll show you the solution. Okay, so here's what you should have ended up with on that last one. You can see I did my ratio, and I got essentially x plus 2 over 3. Absolute value of x plus 2 over 3 is less than 1. Now, when I went through and I wanted to kind of shortcut this, in order to do the shortcut like I was talking about before with finding that interval of convergence, see how I got rid of that 3? because I want to be able to think about the distance between x and some number is less than some number. So I multiplied the 3 over to the right-hand side, and now I can see that the distance between x and -2 is 3 units. So I know my center point's at -2. I know I can go 3 units in either direction. So that's where this came from. I didn't actually break it apart and solve it. I just interpreted what it said. And I also know the radius is 3 based on the 3 showing up there once I got that in the appropriate form. Okay, so now the next part of this, I know the interval, but I need to test the endpoints. You have to show what you're doing. So first of all, I denoted I am testing this at x equals -5. I am testing this at x is equal to 1. And then I rewrote my series with that plugged in, and then I showed that it diverged, and I also justified how I knew it diverged. Same thing over here at x is equal to 1. I rewrote it, and then I showed that it diverged, and I explained how I knew that it diverged, and from there I have my solution. So there's a lot of little pieces to this. It's just like everything that we do in this unit. None of these individual steps are hard. However, there's a lot of steps. There's a lot of places to make a mistake. And there's a lot of little things with notation that you're going to have to be careful about. So I didn't give you a long assignment on this. I gave you a few. But the idea is you've got to really work through these methodically and show all of your work all along the process so the person looking at your work can understand what your reasoning is behind what you're doing. Okay, so when you're doing the homework, keep in mind, right now we've sort of detached this from what we've been doing. We're kind of doing this as a standalone exercise, finding the radius and interval of convergence. What we'll start to look at eventually is writing the series and then finding the interval of convergence of that series that we have just written. So this is like tacking on to the end of what we did last time where we wrote the series out. This will be the next step. And then after that, we can actually use our series to do whatever we need to do with it, whether it be approximate a value for our function, differentiate, integrate, whatever we need to do. So we're just sort of building these series a little bit at a time. Okay, so you've got what's in Wiley Plus as homework. I also attached a worksheet here for some extra practice. So if you feel like you need extra practice outside of what's in Wiley Plus, this is just a worksheet with 5 questions on it. You may not need it now, but you can always use it as a review for your test. It's up to you. This is not something you have to turn in. I just wanted you to have access to some extra practice problems.